Okay, so given your parallel transport structure from given a linear isomorphism from t at gamma of 0 of m to t at gamma of t of m, we can construct a linear isomorphism between t star at gamma of t of m to t star of gamma t star at gamma of 0 of m. Okay. How is this done? Well, you just take a one form at gamma of t consider a one form belonging to the cotangent space of the manifold at the point gamma of t. We're going to send this one form to a one form on the cotangent space of M at gamma of 0, and namely the image, this one form at t star of gamma of 0 of M. If you give me a vector at the tangent space, x, let's say, you give me a vector at the tangent space at gamma of 0, this one form takes in x at gamma of 0, and the output is the one form at gamma of t evaluated. The one form at gamma of t eats the parallel transported vector. So you take the vector x at gamma of 0, you parallel transport it to gamma of t, and then you evaluate that with your one form at gamma of t. Okay, so let me just show you that. So again, these are the lecture notes by Professor Zuoqin Wang. This is lecture 6. Okay, so we have our parallel transport map, p gamma of 0 to t, from t gamma of 0 m to t gamma of t of m, and then by taking the dual, we get an isomorphism of the cotangent spaces. Okay, and how is this constructing? Well, I'll show you. So basically, this dual map here, okay, p star from t star gamma of t to t star of gamma of 0, this takes in a one form, p star of omega at gamma of t, and now we're claiming that this is a one form at the cotangent space at gamma of 0, so it should eat a vector at gamma of 0. And what do we evaluate? What is this expression? Well, this is just omega at gamma of t evaluated at the parallel transport of this vector x at gamma of 0 to the point gamma of t. Okay. All right. So now, given this this dual isomorphism, we have essentially a way to parallel transport cotangent vectors, but in the opposite direction. Okay, and so we can just define the covariant derivative of a one form omega in the direction of a vector field x to be the limit as t approaches 0. Well, okay, first of all, excuse me. Let me just state this better. So we're going to define the covariant derivative of a one form omega in the direction of a vector field x at the point P on the manifold. So let's evaluate this covariant derivative at the point P. We're going to define it pointwise. Okay. To do so, we're going to fix a curve gamma such that gamma of 0 is equal to the point P, and gamma prime of 0 is equal to x evaluated at the point P. Okay. Then we're going to take this curve gamma and use our parallel transport structure, and we're essentially going to evaluate the one form omega at gamma of t. And then using the dual parallel transport structure, we can transport omega at gamma of t back to gamma of 0. Then we're going to subtract the value of the one form at the point P, which is gamma of 0, and we're going to divide by t, and then take this this difference quotient and send the limit as t goes to 0. Okay, and that'll be the definition of our covariant derivative. So again, nabla x of omega evaluated at the point P is equal to or by definition, the limit as t goes to 0 of p star of omega gamma of t minus omega p all over t. And now let me show you the formula. So here it is right here, okay? So you can pause the video and just take that in, okay? And now actually we're going to kind of look at the calculation. So we can use this heuristic, or it's not a heuristic, it's a geometric definition of what the covariant derivative of this one form should be. And then we're going to use the linear connection that we're given to derive a formula to rewrite this difference quotient and actually solve for it in terms of the linear connection on the tangent bundle. Okay. All right, and I will continue this video in a moment.